All right, everyone. Hello. Welcome to today's Friday office hours. Maybe we'll call it office hours. And I just made this quick meeting just because the 3:30 peeps are saying, "Hey, yo, yeah, might as well have one." So, what questions did we bring for today?
I was confused on what to do for the homework number one.
Homework number one.
The exercise one, yeah, for the computer assignment.
All right, wait. Let me see. Uh, let me see if I can get a function where I can see who's actually talking or.
That was Michael.
Oh, that was Michael. All right. Uh, wait, can you see this? No, I don't think so. So let's just pull that up. Alright. Go. Boom. So this one, number one?
Yeah, just for the H of N. Did you want us to find it
The way Dr.
with
Siri does
getting
it?
yeah.
In reality, this is the reason why I said in terms of, I was supposed to put in terms of impulses in itself, um, is that I think it would be a little too difficult to then do number two. So if you do number one, point is, okay, there's an actual way I wanted to show you guys how to do number one, but it would be completely unreasonable. Well, it's not unreasonable, it's just a lot of math. And the one thing I would like to talk to you guys is about, do I want to explain this right now? Yeah, explain it right now. So, where's that assignment? Let's pull it out again. There we go. I'll put it on the side and hopefully everyone took a mental picture of that. So we have our y then is minus 2r cosine of omega naught yn minus 1 plus r2 r squared yn minus 2, which is equal to r sine omega naught x of n minus 1. Let me check one thing. I'm having a quick panic attack. Am I recording? Yeah, it says I'm recording. Is it recording my microphone? Hopefully it is.
2 times n plus 1.
Wait, give me a moment. I'm trying to figure out if my microphone's working. Hello? Oh yeah, it is. It's, okay, never mind. Alright, sorry. If you want to see what software recording I'm using OBS, so now you guys know what I'm doing on my end of the screen. Point is, I had some weird software issues, and I'm actually happy that it kind of works for now. So, okay. We have our system, right? And there's two ways of doing this, but I'll show you the easier way. So we have x of n, we have our system that we probably don't even know what it does, and y of n. However, there's a special trick that you guys can learn, which is, you'll probably learn that, I think maybe next week, or next week is, or the week after that is, let's draw a block diagram, but I'm not going to draw the block diagram that we have here. However, I will draw a direct form one block of it, which is pretty easy. Delay, and you can draw some game, plus, and there we go. Make sure you draw your arrows so that you figure out where your water goes, plus, and because I know what's going on right here, delay. And you're probably all going crazy saying, that's not a game. This is, call it a, what do I want to call this one? B, there we go. And then this one's A, there we go. And then draw your arrows to make sure you know where the water is going. So you're probably saying, oh my goodness, how did I draw this? This is a direct form 1, df1. And it's basically really simple. All you do is, well, you have your delays, you have multiple delays, your input is literally being stored somewhere. That's the mentality that I have. However, with the direct form 1, you're only looking at, well, I don't know how else to explain it, your feed forward and your feed back path, where your inputs, your current inputs and your current outputs are being stored into your system directly. They're not being modified, they're not going anywhere. So if you were to continue this chain, then you're literally saving current inputs, or you're saving current outputs. So that's how you should be naturally drawing your direct form 1 blocks. If I were to give everyone a quiz on some crazy system, everyone should be able to like draw this in maybe 2 minutes or 1 minute without looking at their notes. The direct form 2, it's simple, you just gotta flip it. However, it might be a little visually harder to see that, but the transposed one is really, let me see if I can do this one. X of n, this is literally how I think of, I think of this like finger effect, and the gains. B1, B2, B3, where literally your inputs are directly being multiplied. They're being multiplied and they're ready to be processed into something. So for this assignment, we only had to do a direct form 1 block. And when you're talking about the equation, so here's the thing. And I'll pull out the good old, let's try this marker. We have our, friend right here who's gonna kick this system, kick this system with a Dirac delta or Kronecker delta. I always keep saying that. You have a 1 that's being here, that's going through your system, but right now we're just gonna analyze this part of the system. So, here's your feed forward path. When you throw a 1 here, it goes directly into, well, your output if you didn't have this circuit right here. However, you have this 1 that's getting stored, gets modified by this gain, and that also goes through. This is a feed forward path, so here's a much more simple way of explaining this if no one's getting this. Let's go to page 2. However, for consistency and cleverness, let's do this. Go. Let's bring back our system again. X of n. H of n. And this is a really simple concept that I want to get into everyone's heads, and I don't know if you've already seen the video, which is what's the output going to be equal to? The output is always going to be equal to the input convolved with your impulse response. And suppose we were to kick this box, and the trick with when you convolve anything with the when you convolve the delta function with anything, you get the anything. So this basically means, okay, and I'm gonna show everyone right now, it might actually be a little confusing. Let's flip this. H of n is equal to y of n, or actually now I think this was easier to see. So all you're gonna have to do is, you see this? You replace this, or you replace this with this, and then you replace this with this. So let's get back our old system. And there it is. And all you're gonna do is just h of n minus 2r cosine h of n minus 1. And oof, I forgot some stuff. But point is, you replace all this with h of n based on this relationship right here. And then here's our input right here. You replace this with your delta function. So that's the simplest way of defining the equation. So it's literally a direct form 1 block. You're literally replacing your y's with your h, your x's with your Dirac, no, not Dirac, your Kronecker delta. I'm going to call it delta function. It's easy to say that way. My point is, that's the easy way of approaching that. There's a second way. However, this second way is a little too difficult, and if you were to do the second way, it would actually make number 2 much more easier. However, to get to that equation, it might be a little tougher. So with this, the consequence of this, or replacing all these terms, these y's with h's, is you're going to have to do some crazy mathematics, as in you're going to have to solve for your h at every point. So to make sure everyone doesn't feel too much pain, well, you have to trade pain with pain. I want everyone to solve for your actual impulse response at different points, rather than going through what I'm about to show you right now. So let's bring out a system. Yeah, let's go ahead because I know no one's gonna. I don't recommend. I'm grading this one really simple. Number one's gonna be simple to grade. Number two is where I'm gonna be giving the more points. Actually, this is my scrap paper. Let's get out the. There we go. Second sheet of paper. Let's do this. Y of n minus 2r cosine omega naught, which is a constant. Y of n minus 1 plus r squared y of n minus 2, which is equal to your input, which is, darn, do you think I remember? R sine minus r sine omega naught x of n minus 1. So just in the video that I've shown you before, if you've already seen the video on the impulse response, there's a way to find this total response, and that is basically if we were to have this H system, we can actually split this up into X and then H zeros, H poles, and let's call this one C of n. And let me show you the, if you don't believe me, let's go back to here. What does this look like right here? Ah, see? This system that we have here looks like this. So this zeros is what we have here, and then these poles are right here. How do you get the direct form too? You just flip these two systems. Boom. However, the positive of that is that you can see your memory system, or you reduce your memory size if you were to flip these two. So usually the arithmetic is to flip the poles and the zeros so that you get less memory. This is the practical purpose of, well, you know, you have your poles before your zeros. The negative is, well, you're going to have instability in your poles, and then your zeros might go crazy too. Your zeros get unstable too. And then the direct form, the transpose, it just meshes these two, but I won't show that one. That might be a little too practical, but we're trying to get this type of system right here. So if we were to analyze this, the zeros is going to be this feed forward path. But what is this feed forward path? This feed forward path is this r sine omega term. So let's draw that right now. There we go. X of n plus, and I won't finish this problem actually, because we only have one delay. Let's go this way. There we go. Actually, no, that's wrong too. Let's take it slow. We have an input. We have an input that's going to get delayed by 1, and it's going to be multiplied by some gain factor, which we will call r sine omega. However, we don't have any form there. And if you have OCPD and you draw it like this, well, I don't blame you. But if you do this, where you draw this straight line, that's a -1 right there. But actually, you don't even have to draw this plus sign. This literally just feeds through. This is your system right here. So now you're going to kick this system. Let's call this one C11. You're going to kick the system. You're going to kick this system. And what comes out? So that means your C of n, when you kick this box, is literally going to be your r sine omega naught delta of n minus 1 because it gets delayed. But this, we just said, was whatever the output of your zeros are. So actually, if you don't believe me, actually let's just do it. Let's just say we don't know what's going on. So let's C of n is equal to our input. We just threw our input right here, convolved with h of zeros. What happens when we convolve a delta function with anything? We get the anything. So that means you've already found your first thing. You've already found your impulse response. Your impulse response, and let's get the other marker, is literally whatever comes out of your node. It's whatever comes out of here. So does anyone have any questions on how I got to this point? No one's going to get confused on the exam when they say or everyone is able to find h of zeros. Everyone knows where it's coming from, the practical purpose. Any questions? No, man, it's pretty easy. Alright, next part. Just kidding. So now we already have our zeros, but now we gotta find poles. Let's do the following. And for consistency, 3. So, pull out this guy. Now let's draw our second system. So let me see, where is it? Aha, perfect. Gotta have your equations up and ready. Just because I'm a little adventurous, let's just do it again. Everyone likes consistency. Minus 2r cosine omega naught y of n minus 1 plus r squared y of n minus 2 is equal to, well, whatever comes out of there, but let's call it c of n. C of n, there we go. So let's draw this system. So this system, well, do I want to draw this? Yeah, let's go ahead. So we're going to have some input, which is c of n. See that? So just take a mental picture of this. C of n. And now we got to draw our poles. But our poles is literally going to go feed back. So the one thing you got to do is draw your y of n. We're feeding back. We have to have a delay. We have one delay, which is this guy. Actually, this guy right here gets multiplied by 1, so that's easy. It's a wire. However, there's a rule with this, and it's hard to see with this one, but let's see, how do I want to show you guys? Okay, let's do it. C of n plus 2r cosine omega naught minus r squared y of n minus 2. So how do you tell what signs go here? So it's hard to figure out, well, I don't know, maybe it's easy for you, but for me it's a hard time. So we look at our y output. We look at whatever is our y. It's going to have a positive Cn, and then it's going to have a positive. If we walk backwards, let's walk backwards, and let's just do this because we don't know what's going on. Let's walk backwards, and we're going to have a positive 2r cosine omega naught. So now we know that sign, but now we got to walk even backwards again. Let's put another delay. Let's walk backwards for the sign. Y of n is going to equal a minus r of 2. There we go. So everyone's able to do this, I guess. I'm actually, the reason why I show you this is because I'm assuming everyone by now has already taken the exam, I think, last week. So this shouldn't be that difficult. So I won't be grading harshly on number 1. Number 2, I will be grading pretty vigorous. But everyone's able to do this. Everyone's able to get their poles. So now the next thing we're going to do right now is, well, we need to solve for h of poles. So one thing we're going to do, but I'm not going to finish this because it actually gets pretty complicated, and I don't even know where to go with this problem, but I'll show you how to start this if anyone wants to finish it, but this is not a part of the assignment. So this is the reason why I won't be grading. Like, number 1 is going to be easy to grade, however number 2 I would like everyone to try to solve for the actual impulse response, like point by point, not just the whole equation, for simplicity. So this is a trade-off between difficulty. We're going to kick our box, and here's the problem. When we kick our box here, let me actually show you right here. We're never going to get, well, a complete response. We're never going to get, you know, a one that gets into the system. It always gets involved with some, so sine right here, sine omega is going to be some decimal number that's less than 1. However, this right here can be maybe 3 or 5. That can also increase the gain. However, it's always going to be attenuated by this. So we're never going to get a 1 here. However, and that's the reason why I can't really do this problem completely, because of this condition that we have an attenuated problem. But let's just try it. Let's just try it. We're going to make this one an impulse. We're just going to kick our box. So now what happens? That means our y is going to have a 1 here at time is equal to 0, so let's do this right here. How do I actually no. Here's the other thing I want to show you, and this is the reason why I'm not going to make everyone do this. It's because this right here, if you've taken Dr. Baker's classes, is known as a resonator. These are these puppies right here are the best circuits you can ever have. Like, you know, you have your frequency here, and it does this. This is your response for a band pass filter. It's a band pass filter, a resonator. It resonates at some frequency, F over F of S, 4 F of S or something like that. Here's your Nyquist frequency. Oh yeah, this is a complicated stuff. But the point is, this is the topology of a resonator. And there's a special equation for this one. So if we were to analyze this, I talked about the auxiliary equations. That's basically where we turn our input. It's off. We're turning off our inputs. And we're just analyzing this right here. So the trick is you replace all the delays, or you can do the other way, with lambda to the minus n. So right here we're going to do y of n, but that's just lambda, or not lambda, it's 1 by natural response, sorry, minus 2 of r cosine omega naught, y of n minus 1, just in case you don't know what's going on. Like, I was thinking you could have done lambda squared, but I'm going to try and show the theory beforehand, plus r2, what the lambda go here? Oh, we have a lambda to the minus 2, which is equal to 0. Your auxiliary equations, you have a homogeneous equation. No sources, it's just pure natural response. This is where the complexity starts. And the natural response of this is, you probably won't guess it, but it's going to be r to the e to the minus j omega. Where's our lambda? Our lambda is, actually, let's replace this one right here. Lambda squared minus 2r cosine omega lambda plus r squared. There we go. This equation would be lambda, the zeros for this lambda is going to be this, and r e to the positive j omega. That means your lambda is going to equal r e to the j omega plus or minus. This will be your zeros, and this makes sense. I will show you a quick concept. This right here is a phase shift. It's going to be some type of angle. You're going to be creating some type of angle with a unit circle, if you remember from Euler's equation. This right here is just going to be the angular distance, omega, from your real axis. I'm going to call this real axis. Yeah, it's going to get complicated right now. So that means the location of this pole would be right here. Let's draw an X. Consequently, if you remember that word, we have a pole right here so that they balance each other out at minus omega. So that means if we were to analyze this from 0 to, you know, our maximum frequency, that means this, for this type of special system, depending on omega, maybe omega is pi over 4. So that means your response would probably be something like this. And it will resonate. So this right here is a good way of seeing, oh, it's a bandpass filter. So this is the reason why I'm not going to make everyone do this. I see this all the time when I work in, you know, the little research places I work at. So actually, if you wanted to keep going with this, let's keep going with this. This is why this is all optional office hours. This is all just supplementary. We have a general equation. This is how you're going to do it. So we have some general equation. We don't know what it is. And let's do this. We're going to have some C1. And yeah, let's just do lambda 1 to the n plus C2 of lambda 2 n. And then all you do is just replace the lambdas that you found. So I of n, C1 of r e to the positive j omega plus C2 of r to the e to the minus j omega n. There we go. So now we kicked our box. We kicked our box at time is equal to n equals 0. So that means if we were to model this is y of 0 is equal to 1. We just kicked our box, but we don't know what it does. And we're going to have to do c of 1, but this right here, this n right here is going to be 0, so that means this whole thing is going to be 1 plus c of 2. That's going to also be a 1. So this right here is, well, your little equation. But this is the reason why I'm not going to go over the next point, because now it starts getting messy. We just kicked our system, but now we don't know what's going to happen after that. And I think it has to do with the memory equations that Dr. Stubert has given us, but I'm not going to do that, because that means it makes this class unreasonably harder than it should be. Where I would do this is equal to c of 1 r e to the positive j omega plus c of 2 r e to the minus j omega. And if you want to do this nasty math, I think I got a sync response? No, I don't think so. But point is, it gets pretty complicated, and that's the reason why, instead of doing all this, but this is naturally how you would find it, but with this problem, I don't think so you guys are going to build resonators. That's a graduate topic that we like to have. I don't have my book on me, but if anyone wants to read this book, if you guys don't believe me, let me see. Let me get this out, just because everyone's really interested. Like, why is David talking about all this? Oh yeah, you guys see that? Let's type in resonator. There we go. Boom. And this is your, and oh, look at that. Oh, look at that. We have our general equation for our resonators. So don't be afraid of, you see these Z's, yeah, this is a little concept, but point is, this is your basics to high pass filters or your low pass filters, your resonators, and I will show everyone how to use this plot. It's going to be supplemental. You don't have to learn it, but if you learn it now, here's a good quote. You either learn it now or later. Guess what? It's later, so you'll eventually all have to learn how to actually use this circle, what it means, and what to do with it. But let me go back to what I have, the screen. This right here is going to be our fundamentals into resonators. So that's the reason why I'm made this number 1 much more easier, which we can go back, I think 30 minutes ago, which is to replace all your y's with h's, all your delta functions, or your x's with delta functions, and then we're going to go to number 2. Let's go to number 2. Let's pull out another piece of paper. Oh gosh, I'm running out of paper. Sweet. That means I'm learning, or showing you guys a lot. That's good. What page did we just leave off of? Page 4. For consistency. Page 5. Yep. Like professor, like student. 6. There we go. So now we built our system. Let's do h of n is, actually let's just do it from scratch again, just to make sure everyone's following. So we have our equation right here. I'm going to rewrite it again, but now we're just going to flip everything. We're just going to switch everything with deltas and the impulse response itself. 2r cosine omega naught. And actually, because I get tired of this little thing, you can actually make this one like some variable. Let's define this one as I don't know what's a good variable. What letters? There's a whole bunch of letters. Alpha, let's go. And alpha 1, there we go. Plus R2, which I will define as alpha 2. Do I want to do this? Nah, let's just show the whole thing so that no one gets lost. Oh, oops, I forgot this one. H of n minus 1, H of n minus 2 is equal to R sine omega naught delta of n minus 1. And there you go. So now we got to solve for, well, the easiest part of this assignment, which is h of n is equal to r sine omega naught delta minus 1 plus r2r cosine omega naught h of n minus 1 plus or minus r2 h of n minus 2. And the one thing we can do right now is we can apply the Schwartz inequality. That's what it's called. Remember, y of n is going to equal 1 minus infinity of h of n x of n. If we were to apply this, the Schwartz inequality would be that this have to be less than or equal to h of n from infinity to minus infinity, n is equal to, sorry. So the one thing I want to tell everyone is we have an impulse response. Well, it's a function of deltas and h's. We're throwing 1 volt. And let me just draw this little system right here. X of n, y of n, and we're throwing 1 volt. So an impulse response, if you actually wanted to build this up, there's a conversation that Dr. Baker and I had, and Dr. Stewart too. Cyber Union was there too. They were presenting some type of system, and they were talking about convolution and communications. And Dr. Stubru was saying, oh, I know how to model this sampler. We can just use, we have some little sampler thing we have. We can model this as, delta functions. And then when Dr. Baker heard that, he was like, delta functions? Can you build that? Which is like a little spike which goes to, like, the biggest value at a small instance. Yeah, he tried building that. I think he's making us build this in his 700 level classes. But the point is, to model this, we just look at the maximum voltage, which is going to be VDD, and we're just throwing this into our system. But because this is discrete, here's time is equal to n is equal to 0, and then at n equals 1, it's, 0, and then the time before that's 0. So we're just throwing the maximum voltage, which is VDD. The infinity voltage is what we call it, is VDD. The max that y of n should be, or could be, is going to be VDD. So what you're going to have to analyze is this right here, and all you got to do is you got to add all these points. All these points. So at y is 0, or h is 0, you're gonna do, well, what is the delta function? Actually, let's just do it. Sine of omega naught. The delta function at, well, let's do this. N equals 0, and it says delta function will be minus 1 plus 2r cosine omega naught h of minus 1 and minus r squared h of minus 2. So what's this right here? This right here, well, I just showed you right here. What's so complicated about that? This is going to be 0. See? And then this right here, well, okay, we're assuming that this box, nothing's in it. We don't know. If I move this box and give it to you in the future, well, there's nothing other than a VDD and a ground. We don't know what happened beforehand, so we can always assume this is 0. Whatever happened before this has to be, well, we haven't kicked our box yet. This hasn't even sensed, so this can be naturally 0. This can be naturally 0. So if h is 0, it's going to have to equal 0. So that's your easiest point. The whole purpose of this, the whole purpose of me trying to show you to replace this with your delta functions and maybe your impulse response, the actual h functions, is so that you can visually get what's going on. Okay, if I were to give everyone a little quiz and I say, okay, in the time domain, plot for me the impulse response, everyone should be, oh wait, with this system, okay, then that's you're ripping me off, man. At this point, h is 0 is going to be 0. So now the next thing we're going to do is we're going to have to analyze h of 1. Now this is where the fun part begins. So now this function, let's do, here's your n is equal to 1. is going to be r sine omega naught. So this function turns into 1. And then we have 2r cosine omega naught h of 0. But we just defined h of 0 as 0, so this is gone. And we can forget about this last term because that's obviously going to be 0. So that means h of 1 is going to equal to r sine omega naught. So now this is the next point right here. So if we were to draw 1, then we can plot this value right here. There we go. And then I'll just write r sine omega naught is that value. And then you would keep doing this iteration, you know, h of 2. Here's the fun trick about these delta functions. Once you use it, you never have to use it anymore. So right here, if we can analyze this term, what happens at n equals 1? Or n equals 2? 0. And at n equals 3. This is also, so we can just completely forget about this term and just analyze the natural response of our system. This is gone. This right here is already in our system. This will be accounted into our system. So if we were going to look at h of 2, we were going to look at h of, so 2r cosine omega naught, h of 1, which is going to be this term. And then all you do is just you keep doing this iterative process, and then let me just complete this problem. Minus r squared h of 0, which is going to be 0. This process would keep iterating. I'll just draw this right here. And I'll draw this right here. Draw this right here. And you can plot this by hand. And then you're saying, oh, what about the stability criteria? You see this right here? You add every point, all these points until you hit something greater than 0. You're probably going to see, oh, look, at this time, and adding all these points up to, well, whatever we have, you'll see some stability criteria. If you don't believe me, here's at 2. We're probably going to be here. However, our VDD, or 1, is what we're going to call it. This is the point we're going to be analyzing, actually, okay, because it's getting a little messy. There we go. You're going to have a situation where, let's just bring out the different color markers. Here's a 0, 1, 2, 3, and I'll just finish it. You know your first point's going to be here, your second point's going to be here. Our next point, I really don't know where it's going to be, so it's going to be maybe, you know, between this range right here. Then here's our 1 volt, or 1. Now this is the point where we have to start analyzing stuff because I don't know where this might hit 1. The minute this hits 1, then we can actually look at R value. Where's our R value? R. So this is where you start looking at your stability criteria. And there's one thing I wanted to show everyone, because I just literally saw this from the previous videos. Let's see. From actually looking at this, let me see. I'll pull out a system right here. Go. So I'm gonna bring out a new system. So actually, point is, this is how you would analyze what your R value is in by hand. So you're gonna have to look at, you're gonna change your R. Maybe this might be R is equal to 0.8, and then right here might be R is equal to 1.2. Then you got to figure out what R values. Actually, let's say right here you might get R is equal to 0.7, which is stable. Or let's talk about the easy one. Or R is equal to 0.1, super attenuated, which is easy. So that means your R has to be, for this to be stable, R needs to be less than or equal to some value. Let's call it K. So that's your value you're going to try and find. And yes, this is possible by hand. I want to make sure everyone knows how to do this by hand. If I were to give everyone a quiz on this, everyone can naturally find this in terms of this. But I will show everyone this type of system. Yeah, we still have a couple good minutes. So let's pull out another piece of paper. I'm going to bring out an old system that I've talked about in a previous video, and I'm just going to get to the solution right now. So here's the system that we have. It's equal to x of n plus beta x of n minus 1 minus alpha y of n minus 1. And this is a system. And from a previous lecture, and you can watch that if you want to see the solutions to that, we figured out that the h of zeros is literally, well, just by looking at this, we can look at this input right here, which is going to be, a moment, delta of n plus beta delta of n minus 1. Our h of poles is going to equal minus alpha of n unit step of n. And you're probably asking, why do I do the unit step? Just based on what I was saying beforehand, h, y, x. We don't know what happens beforehand, like n less than 0. We don't know what happened beforehand. But everything starts the minute we throw this kick in. So that's where we start analyzing this. We don't know what our system does beforehand, so let's just force everything to 0. With this, everything before n is equal to 0 is 0. So we don't know what our system does. And that makes sense. Our system doesn't do anything until we kick our system. So there's one thing I wanted to show you. H of n is going to be h of zeros involved with h of poles. And that final solution that I posted in the previous video is minus alpha of n, u of n, plus beta minus alpha of n. Actually, this might actually be a bad example, but actually it's a okay example, where you can actually brute force the Schwarz inequality this way. So look at this term right here. When does this start blowing up? This term right here. The minute alpha gets bigger than, okay, so if alpha right here, alpha is equal to 0.99, then if we go n is 1, that means 99 times to the squared power is going to be something smaller than that. So the more we, the higher this exponential or this n value, this is always going to be decreasing. This function right here is going to be decreasing. However, when alpha is equal to 1.01, this is where we start seeing that problem. What's n? What's 1.01 to the second power? Oh, you get something bigger than 1. Oh, actually, you don't even have to do that. What's n equals 1? At n equals 1, what's the value for this? You get 1.01. However, then you would have to analyze this term. And then you would say, okay, so now we have a second attenuator. We have the second variable, b, and then you have to analyze all this. It's all a crazy criteria. But the point is, this is how you would directly solve using the Schwarz inequality your values. So if you were to do h of n minus, there we go, plus infinity of h of n, you would analyze that based on this one. If n goes to infinity, this term is your term that you should be worried about, and then this term right here too. But I think this one would be more of a problem than this one, because this one's an attenuator effect. This might be like 0.2 or something like that, but this one will grow faster than this one. So that's how you would easily use the Schwarz inequality for that one, and hopefully that's actually will help you with the exam, this term right here. So hopefully that didn't maybe that opened everyone's eyes, or maybe that made a few of you guys go, well, what the hell is this guy talking about? Don't worry, you guys will figure that out. But are there any questions regarding what I just mentioned? Is this a good help, or did this actually open everyone's eyes that this is buildable? You can build this in digital or your analog domains. Or any more questions, complaints? Why are we extending why are we asking for an extension? Because I've already given everyone 5 days, and I think it's a reasonable assignment. If you've done exceptionally well on the 3rd assignment, this is the reason why I edited this 4th assignment. Let me show you right here. There we go. Job conflicts, then you'll have to email me that and we'll talk about that. But however, if you were to do this system right here, everyone can, build this one. I know everyone can do this one in well, 2 minutes if I were to assign a quiz right now, but I'm not going to do that. This right here, well, I just literally showed everyone how to do this right here on my piece of paper right here if you wanted to see that. And then number 3, well, you're just building a direct form 1 block, which you've already got from here. If you can do this by hand, then I can definitely trust that you can do this on a software. Don't worry, if software is hard, then yeah, don't worry about this. However, I want to make sure everyone can do this by hand. I want to make sure you know what's going on, how to implement these systems. And what's so hard about this? This right here is just your attenuation coefficient. And oh, maybe this actually might help for number 2 too. So this is the reason why I say if you know what's going on in number 1, know what's going on in number 2, and 3 should be a really implementation. You only have 1 variable. This right here, well, you've already seen from the previous assignment that if you already know how to store your states, you know how to store your states. So I'll show you guys right now. Go. If you were to have some, y of n vector, I'm not going to show everyone this. Let's do it in MATLAB, I think. If we were to have a vector, let's do this. Let's do this right here. I'm going to have an n vector, which is going to start at -2. So this position right here is going to be -2, -1, and 0. This is going to be array value 1, array value 2, etc. But however, I'm going to have some vector right here. Here's your y vector. That means if you want to store something here at, let's see, what do I have there? At y of -2 is equal to -r2. All you got to do is just boom. So -r -2 sine to the 2 omega naught. And then you would store whatever is here. Easy. And that's how you would build your thing. Hopefully no one's just copying the code and saying, oh yeah, this works. I want to make sure, like, there's a reason why I have this part called pre-length. And if you understand what this is, we're just saying, oh, here's some pre-length before this thing. We know how to set up these numbers. We know how to set up these numbers. That's the reason why I have that variable right there. So once you get this system set up, well, this system right here, actually, no one can see my screen. This system right here is all set up in question number 3, which is, pull that up, which is right here, question number 3. And then if you get number 3 good, number 4 should be, well, simple variable change. And this right here is not that bad. All you're doing is you're looking at the impulse response, which is the kick, your impulse, and memory. But note, this system right here is actually an impractical system. This system right here is impractical to build. So don't worry, and this is the reason why I made number 4 and number 3. If you do this, max abs difference, they should probably be the same. So that means what you're going to see is you're going to see a double result. But point is, the whole point of this is to figure out what, well, I can't say that too much, but point is, that's your response number 6. So in terms of the extension, I think I've made the assignment due midnight, so make sure everyone has it done by midnight. However, you can still submit it after that. I'll be looking at all these assignments tomorrow, Saturday, around 10 a.m. So if you are working on this at 3 a.m., yeah, do be my guest, submit that. So point is, if you can't get that turned in by midnight, well, you still have until 10 a.m. tomorrow. So that's the little rule that I've given. But after that, the due date is the due date. If I were to have a project, if you have a boss, you like your job, and they're saying, I want this project due now, they can't give you a pat on the back on something. But point is, go do your work. However, a due date is a due date. Everyone had 5 days to do this, so hopefully no one's starting it today. Oh wait, we are. Oh, it's okay, but you do have until 10 a.m. tomorrow. However, it will be marked late, so to get all the full points, this should be one of the easiest assignments. I've edited it so that it's not so difficult, that everyone can probably finish this. I could finish the assignment in 30 minutes, but everyone should be able to do it in an hour. So with that said, are there any other questions or Concerns? How's that exam? Are y'all good for that exam? I think you're going to have impulse response. Basically what I just said, you're analyzing your individual terms. You know how to build this. However, this is just a digital domain. I can't really explain too much about the analog. However, it's the same concept. You kick your box at the impulse, and then you analyze your equations. So I can't really help with the analog as much. That's going to be something you all have to do as homework, or not homework, but more as a study thing. However, this is the most practical explanation I can give everyone about how to build this system, how to analyze this system. So in the next lecture, and this is the fourth assignment, or not the fourth assignment, the fifth assignment, and I think the fifth assignment has to do with, or one of the assignments, is we're going to have to talk about z-domain. And suppose I were to do, okay, so the rule about this is, just if everyone wants to know, is we have some input, which is equal to x of n, convolved with our impulse response. However, there's a beautiful thing that we have, which is the z-domain, which says, okay, I'm going to go through practical stuff, by the way. If this is confusing, don't worry. You'll learn about this eventually. Where to take the z-domain, all you got to do is replace the y's with the z's. Convolution in the time domain is going to be multiplication with z-domain. And then where does everyone see this from? And this is what I want to get to everyone. And then you're like, holy crap, what's going on? And you're going to be saying, oh, this guy's going to have some, poles and zeros. You're going to see some poles. However, this actually is going to be flipped. You're going to see that in a second, but don't worry too much about that. But point is, let's say we have some system right here. Let's call it h of z, which is going to equal 1 minus e to the minus 1. So if I were to give you this type of transfer function, we notice that, well, there's going to be a 0, well, at 1. However, let me just do this to multiply this by z, divided by z, 1 z to the z minus 1, divided by z. And Dr. Baker gave this on a quiz, and you want to know how many people got this wrong? A lot of people, because they're like, oh, we have this thing, hooray, there's only 1 0 right here. Nuh-uh, you have a pole right here. So this right here says we have a 0 at this point. If I were to draw this unit circle, we have a 0 right here at z equals 1. So here's 1. And then we have a pole at 0. So z is equal to 0. Here's your pole. And you would be, you'd be shocked that a lot of people would forget this. Everyone is like, yeah, this is easy. I forgot this. Minus 2. And that was out of, I think, 3 or 5? I don't remember. The point is, this was on a quiz, and no one could have done that. But this is the practicality. Actually, let me show you a crazy trick right now. A trick that no one should be showing you. This is actually introduction to mixed signal design. If anyone is interested in that class, this is offered every 2 years. Let me show you this. So you're used to, your Bode responses, right? You have your Bode plots, and you have some F20, right? And maybe this is 1 or something like that. So this right here is in the Fourier domain. You probably haven't heard that term, but a Bode plot is a Fourier domain of your signal. You're trying to see the Fourier domain, or the Fourier transform of this function. You're trying to see what your frequencies are doing. However, with the Laplace, or your Fourier domain, there's a rule for the z-domain. And the z-domain is that if you looked at the unit circle, you get your Bode response. Oh, you can't see that? So let's actually analyze this point. This is a 0. So if we were to go from this domain to this domain, we will have at the frequency a 0. So that right here is a 0. However, well, I won't show everyone this, but let's do let's call this one 0 and f sub s, I think. Do I want to call it that one? F sub s divided by 2. Yep, f sub s divided by 2. So there's a rule with these things. So you know how we have poles that are like, I'll just draw invisible poles. So if I were to do like a pole right here, and this invisible pole right here, that at this frequency right here, if I were to draw these poles, we will have this. Actually, what does a pole do? A pole goes to infinity. If I were to do this response, it would start like this and then go into infinity. In terms of voltage, V out or V in. Your voltage goes to infinity at a pole. However, we're not going to do that. We're just going to look at this response. But you notice that with poles, conjugate poles, we have a mirrored image on each side. So what I'm trying to get to everyone without trying to, like, give you too much of your value is that we mirror our things. So that means we have to mirror our response. Here's our frequency. So that means the response of this filter is going to be the following. And there we go. And this right here is a Bode response that you can solve for. And this is how you take from the Z domain into the Fourier domain. This right here is, well, a simple, it's actually a low pass filter, because here's the positive frequencies and here's the negative frequencies. Circuit builders only like this domain. The signals people like this domain too, because they can see the total power. If you analyze this, you only get half the power. However, when they're doing signal to noise ratio, half the power divided by half the power gives you 1, which means the circuits people are going crazy, like saying, yay, it works. Whereas the signals people are like, you're missing a term, but it all canceled out. The point is, with circuits people, they just look at this. Signals people, they look at the entire thing. However, this is all a filter response. So that's the extra little thing I wanted to show you guys. But and you can actually find the Bode plot of this if you wanted to as well. This would actually be, there's a trick he'll show you, which is e to the j omega t. If you replace your z's with your omegas, this is how you turn it to the omega domain, Fourier domain. Your h omega is equal to 1 minus e to the minus j omega t, which is also equal to e to the minus j omega 2 over t. Actually, just because you guys got me pretty into this. We'll just finish this problem right here. Go right here. And you'd be shocked that I'm teaching you this, guys, right now, and this is the most practical thing and I've learned this in Dr. You will learn this in Dr. Stuber's class. And I want to make sure everyone, from the bottom of my heart, knows how to do this. Everyone doesn't do this. Everyone takes this, function right here. Let me just write it on the side. 1 minus cosine omega t minus j sine omega t. Everyone does this, and then they try to find this, magnitude. I don't like this, because, it's fine, but it's a lot of math. However, I'm going to show you this amazing trick, which is just keep it in the Fourier domain, in the, E domain. So I pulled out something right here, and then this right here, we do 2 to the j divided by 2 to the j. If you recall from, let's pull out another marker. Oh, that marker sucks. This marker sucks. Let's pull out the golden marker. If we were to do this right here is going to equal e to the j omega t sine. There you go. And then that's a 2j, which is also equal to 2 e to the j omega 2t plus pi over 2. And then where does the pi over 2 come from, you probably ask? J is equal to e to the j pi over 2. There you go. Easy. But then if you wanted the magnitude response of this, h of omega, well, what's the magnitude of 2? This is 2. What's the magnitude of this? What's the magnitude of Euler's equation? It's always going to be 1. And what's the magnitude of this? Actually, why would I think I did something wrong? Actually, no, this is correct. This is right. So, this is how you would do practical mixed signal designs. So this is all 722 stuff that you're learning. But the point is, we use this a lot in the field. We use this a lot in research. I'm building this right now. Well, something much more complicated than this. So are there any questions? Anyone saying, man, David, now you made my life have meaning and purpose. Everyone good? No more questions? Ready for the quiz? No. God, it's okay. No quiz. You guys have already. I'll be giving more quizzes probably the next week to make sure everyone knows what to do with practical signals. I don't want you guys thinking, yeah, this is just a math class. No, I want to make sure this is all engineering stuff, so you're getting your money's worth. Any questions? No more questions? We're all good?
I guess so.
Alright then. Have a good day, everyone. I'll upload this video and the PDF so that everyone has good supplementary things.